In this video, we're going to discuss three different applications of matrices. The first will be stochastic matrices, then we'll discuss some cryptography, and then finally we'll go over linear regression. Okay, so the first type of example is on stochastic matrices. A stochastic matrix is just a matrix where each entry, so it's a square matrix where each entry is a probability value between 0 and 1. A probability of 0 means that something is never going to occur, and a probability of 1 means that something is certain to occur. And in addition, the stochastic matrix should have the sum of each column be equal to 1. So here we have two square matrices where the first one is stochastic because you can see each entry is between 0 and 1, and if you add up the entries in any particular column, it's equal to 1, right? So 1/2 plus 1/4 plus 1/4 is 1, 1/3 plus 2/3 is 1, and then 1/5 plus 4/5 is 1. Okay, so the first matrix here is stochastic, whereas the second matrix here is not stochastic because you can't have negative numbers as probability values, and in addition the sum of the entries in the last column is not equal to 1. Okay, so that's what you should look for when determining whether a matrix is stochastic or not. So what we're going to use stochastic matrices for is essentially they're going to represent transition probabilities, which will allow us to calculate how a population changes over time. So the setup for the situation is the following. So firstly, we're going to have some given population which is divided into a finite set of states, which we'll call S1, S2, up to Sn, and each individual in the population only belongs to one of the states at any given time. Okay, so the second part of the setup is that each entry in our matrix represents the probability of changing from one state or another after a fixed unit of time, say 1 day or 1 year or something. Or the probability could represent staying in the same state. Right, so it's explained in this diagram here, right? So you separate the rows and columns to represent each of the states, and an entry in a particular row and column tells you which state you're starting from and which state you're transitioning to. So for example, here the entry in the second column first row means that you're changing from the second state to the first state. Right, so basically Pij is the probability of changing from state Sj to state Si. So again, it's changing from the state represented by the column to the state represented by the row. Okay, so that's the matrix of transition probabilities, which we'll call P. And the third part of the setup is that we'll have a column vector, which we call x0, which we'll call the state vector. And the entries in the state vector is how the population is divided among the different states. Right, so there's n states, so there should be n entries in the state vector. And then finally, the way we calculate how the population changes over time is to just take the state vector and multiply by the transition matrix P. Right, so if 1 unit of time passes, then we'll multiply P on the left by x0, and this will calculate the state of the population after 1 unit of time, which will represent as x1. And if we want to calculate how the population changes over additional units of time, we just keep multiplying by P, right? So if we take x1 and then multiply on the left by P, we'll reach the state after 2 units of time. But multiplying x1 by P is equivalent just to multiplying x0 by P squared, right? Because if x2 is P times x1, and then x1 is in turn P times x0, right? So then P times x0 is just P squared times x0. And we can continue this for any number of time periods, right? So x sub k will be calculated as P times x sub k minus 1. So each successive state is calculated by taking the previous state and multiplying by P. And again, this is equivalent to just starting from the initial state and transitioning k times. Okay, so this is the basic setup for how we use stochastic matrices. And now we're going to take a look at an example. So in this example, we're going to use a stochastic matrix to try to model how a virus spreads through a population. So you can think of this example as similar to what's occurring now with the coronavirus. Right? So some people have never been infected, some people have been infected and recovered, some people are still infected, and so on. Okay, so let's take a look at this example. Right, so it states that in a population of 200,000 people, 40,000 of them are infected with the virus. So after a person becomes infected and then recovers, the person is then immune. Right? So basically, it means that that person cannot be infected again. And of the people who are infected, 5% will die each year, and the others will recover. So of the people who have never been infected, 25% will become infected each year. And the question is trying to figure out how many people will be infected in 4 years. Okay, so in a situation like this, what we want to do first is to identify how many different states there are for the population, and how to represent those states. Okay, so initially in the setup, you can see that some people are infected and some people are not infected, right? So let's call state N be the people who have never been infected. And then again, some of the people have been infected or are currently infected. So those are the initial states, but over time there are additional states, right? Because here it says after a person becomes infected and then recovers, the person is still immune, right? So some people then recover from the virus. So let's put that as an additional state. So R to represent the recovered people. And also, some people who've been infected will die each year, right? So that's going to be another state of an individual in the population, right? So people who have died. Okay, so we're going to have 4 different states for this population, right? So the people who've never been infected, the people who are currently infected, the people who have recovered after being infected, and then the people who have died from the virus. Okay, and finally, here the setup is from year to year, right? So the time period for one transition will be 1 year, and so now let's set up the matrix for transition probabilities. Right, so what is my matrix P? Right, so I've called my 4 different states N, I, R, and D. Right, so let's label the rows and columns so that I know which entries transition from which state to which state. Right, so the first column is representing the probabilities transitioning from the never infected to the different other states. I is the column for I is the probabilities transitioning from I to the other states, and so on. Okay, so what are the different transition probabilities? So let's look back at the problem. Right, so it says that of the people who are infected, 5% will die in each year, and the others will recover. Right, so these are where the initial state is infected. Right, so it says that so if you're currently infected, then you have a 5% chance of dying. Right, so I to D is 5% or 0.05, and then the others will recover. Right, so if you're infected, then you have a 95% chance of recovering, so that's 0.95. Okay, so what else do we have? It says of the people who have never been infected, 25% will become infected each year. Right, so so if you're never infected, right, so if you're in the end state, then 25% will become infected. So changing from N to I will be 25% or 0.25. And so it doesn't explicitly state it, but we'll just assume that if you've never been infected, then you have a 0.75% chance of still not being infected, right? So that's staying in the end state. So N staying in the end state will be 0.75. Okay, and then what if you have recovered or have died, right? So if you are already recovered, then you're immune, so you cannot be infected again, right? So if you're recovered, then you should always stay recovered, right? So that means that if you're recovered, you're certain to stay recovered, right? So that probably is equal to 1. And if you're dead, well, you're certainly going to stay dead, right? So the probability of staying dead is also equal to 1. Okay, so let's now enter those probabilities into the matrix, right? So if you are never infected, then the probability of staying never infected is 75%, right? So this is n to n is 0.75, and then n to I is 0.25. You can see this already adds up to 1, right? So that means that there's no way to go from never infected to recovered, and at least according to this setup, there's no way to go from never infected to dead from the virus. Okay, and then I to D is 0.05, and I to R is 0.95. Again, this already adds up to 1, so these are 0. And then R to R is 1, D to D is 1, and again, these other entries should be 0. Okay, so this is our transition matrix P. Right, so I've already entered it into my calculator. Right, so the first column is the 0.75, the 0.25, second column is these two probabilities, and then the third and fourth column looks like this. Okay, so this is my transition matrix. Again, this is what it looks like in the calculator. Okay, so the next step is to identify the initial state, x0. Right, so again, we have 4 entries for the initial state. And however you've arranged your states previously for the transition matrix should correspond to how you arrange the states for the state vector, right? So my ordering was N, I, R, then D. I mean, the transition matrix could be slightly rearranged, again, depending on how you arrange the different states. Right, so I've arranged the states in this particular way. Okay, so what is the initial state? Well, it says the total population is 200,000, and out of those 200,000, 40,000 are infected. Right, so 40,000 are infected, and the total population is 200,000. Right, so I mean, because this is initial state, we're going to assume that no one has recovered yet, and then no one has died yet, right? So that means the remaining people should be never infected. So there should be 160,000 of those, right? So the total population is 200,000 here. Okay, so that's our initial state, and again, I've already entered in my matrix here. So that's my initial state vector. So again, this is the never infected, this is the infected, this is recovered, and this is the dead. Okay, so now we want to calculate the result after 4 years. Okay, so each transition represents 1 year, right? So I'll have to transition 4 times, right? So x4 will be p to the 4th times x0. So in my calculator, that's C and D, right? So I can just calculate it quickly in the calculator, right? So C is my transition matrix. So this, I can just raise this to the 4th power, and then I multiply by my state vector, which was D, and this will be the result. Okay, so this is the population belonging to the different states after 4 years. Okay, so again, the first entry is the never infected. The second entry is the currently infected. The third entry is the recovered, and the last entry is dead. Right, so what this is saying is after 4 years, uh, 50,625 still have never been infected. So maybe they practice good social distancing and wearing masks and so on. And then 16,875 are currently infected in year after 4 years, right? So that would be year 5. Then that would be starting year 5, right? So and then the majority, over 125,000, are recovered from after being infected, are recovered and immune. And then finally, 6,625 have died from the virus. Okay, so this was again an example of using a stochastic matrix to model how a virus spreads through the population. Right, so you can imagine you can change the population, what the initial state is, what the different probabilities are in terms of recovering and dying and so on, and you can see how that changes the modeling of the different states over time. Okay, so the second type of application we're going to discuss is using matrices for cryptography. The basic idea behind cryptography is that given some message, we want to encode the message in such a way where those who have some kind of key can decode it and recover the original message easily. But those who don't have the key, it becomes difficult to figure out what the original message was. Okay, so the setup we're going to use is the following. So first of all, typically messages are written in English, and we work with matrices where the entries are numbers, right? So we need to translate the English into some numerical representation. And so what we're going to do is we're going to use this table here to do the translation, right? So the letters of the alphabet are going to be represented as numbers from 1 through 26. And if we have spaces in the message, we'll represent it as the number 0. So this underscore just means that there's a space in the message. Okay, so now that we have the message in numerical form, so how do we do the encoding? So the key that we're going to use is going to be some n by n matrix of some fixed size, right? And because messages can have arbitrary length, but our matrix is going to be some fixed size, we need to break up the message into partitions of size n. So they're going to be represented as row matrices of size n. And so then we'll be able to do the matrix multiplication with our key. However, because again, typically messages can have arbitrary length and they're not always divisible by n, so you can run into a situation where the n of our message doesn't fill up an entire row vector of size n, right? So let's say the message ends in 2 letters or something, but we say we wanted to, we're working with a 4x4 matrix. Then what we need to do is just to add spaces at the end of the message until it fills up the last vector. So you would add 2 spaces to go from 2 letters to 4 letters. Okay, so so now the uncoded matrices have the proper size to do the matrix multiplication. We're gonna, right, so this is the X represents the uncoded message, Y is the encoded message, and A is the key, right? So A is going to be an n by n matrix. This is the uncoded is going to be 1 by n. The encoded is also going to be 1 by n, and you can see that the sizes match up, right? So X is 1 by n, A is n by n, and Y, so the n's match up here, so the Y was 1 by n. Right, so one thing to be careful about here is in this setup, we're multiplying the matrix A on the right, whereas typically we multiply using A on the left, right? So here is A is being multiplied on the right, so we want X as being a row vector, right? So this should be a row vector, and the resulting matrix is also a row vector. And so that everything is the proper size and the multiplication works out. And then you just do that individually to each of the partitions, and then you get a list of encoded matrices Y, and you line them up in the proper order. Right, so by doing the encoding using matrix multiplication in this way, again, as long as you know what the key is, then it's pretty straightforward to do the unencoding to recover our matrix X, right? So here the multiplication results in the matrix Y. So how do I recover X from Y? Well, I just use the inverse matrix A, right? So I mean, if we're starting with XA equals Y, then I multiply on the right by A inverse, because I want to cancel the A on the right. Then you get the equation X equals Y A inverse. And then if we do this multiplication, A inverse to Y on the right, then that'll recover the original unencoded matrix X. And then, well, X is going to be in the form of numbers, right? So then you can just get the original message in letters by using the table to translate it back. Okay, so let's go through an example where we run through the process of encoding a message. Right, so here we're given the message send cash, and we also have our matrix A, which will be the key that we use to encode the message. Right, so here we see A is a 3x3 matrix. Okay, so the first step is to partition our message, right? So because A is 3x3, we want row vectors that are length 3, right? So 3 letters at a time. Right, so we want each to be length 3. Because A is 3x3. Okay, so now we have to translate the letters into numbers, right? So S, so this is the same table from before, pasted here so that it's easy to read off, right? So S is 19, E is 5, N is 14, D is 4, space is 0, C is 3, A is 1, S is 19, and H is 8. Okay, so these are still unencoded, right? Because it's easy to get the original letters back just from the table. So I have 3 vectors, right? So let's call them x1, x2, and x3. And now we're going to use the matrix A to do the encoding, right? So because each of these are row vectors, again, I have to multiply A on the right. So first x1 times A. So what do I get? So x1 was 19, 5, and 14. My matrix A is 4, 2, 1, negative 3, negative 3, negative 1, 3, 2, 1. Okay, so let's multiply this out. So I've already put the matrix into the calculator. Right, so my matrix A, right, so is 4, 2, 1, negative 3, negative 3, negative 1, 3, 2, 1. So that's my matrix A. And x1 is 19, 5, and 14, right? So now let's multiply them out. So B should be on the left, and then A should be on the right. So this results in 103, 51, and 28. 103, 51, and then 28. Right, so this is Y1. Right, this is now encoded. Whereas here this is unencoded. Okay, so that's the first vector x1. So we just repeat the procedure for the other 2 vectors, right? So x2 times A. So what was x2? 4, 0, 3 times A. 4, 2, 1, 0, 3, 3, negative 1, 3, 2, 1. So what do I get? So I've put this one in C, right? So 4, 0, 3, that's the vector I'm trying to multiply. So C on the left, A on the right. gives me 25, 14, 7. 25, 14, 7. Okay, so that's Y2. And finally, I need to encode X3. X3 was 1, 19, and 8. My matrix A again is 4, 2, 1, negative 3, negative 3, negative 1, 3, 2, 1. So what was D? It was 1, 19, and 8. And then, okay, so now I do the multiplication. So D on the left and A on the right. So that gives me the matrix negative 29, negative 39, and negative 10. So this is my Y3. Okay, so the whole encoded string all lined up, right? So would be 103, then 51, then 28, then 25, then 14, then 7, then negative 29, then negative 39, and negative 10. Okay, so now you can see with this list of numbers, if you don't know the matrix A, it's not so easy to recover what the original message was. Okay, so now that I've encoded the message, let's see how decoding works. Right, so first we need to know what A inverse is. So let's calculate that. So A inverse, what is A inverse? This matrix, 1, 0, negative 1, 0, negative 1, negative 1, negative 3, 2, 6. Right, so that's my matrix A inverse. Okay, so now I can just take each of these y's and then multiply by A inverse. So let me store A inverse into, let's say, E. I haven't used that one yet. So that's where A inverse is, and then now I have to enter in the other matrices that I had before. So I need a 1 by 3. Right, so the first one is 103, 51, 28. I need another 1 by 3. That's 25, 14, then 7. Then I need another 1 by 3. So last one was negative 29, negative 39, and negative 10. Okay, so they're all entered into the calculator now. Okay, so how do I recover them? So I just do the multiplication. Right, so first one, so 103, 51, and 28 times A inverse. So let me just write A inverse to save time. So multiplying A inverse on the right. So what is this? was F times A inverse, which was E. This is 19, 5, and 4. And you can see that this was the original vector, right? So exactly what we want. Right, so this was y1. This gave me back x1. And then now y2. 25, 14, and 7. Multiply on the right by A inverse. What is the result? So that was my matrix G multiplied by E. I get 403. So that's x2. Which is exactly what we want. And then finally, I do y3. So negative 29, negative 39, negative 10 times A inverse. That was H times E. Gives me 1, 19, and 8. Which was our last. And then now you can translate the letters back, right? So this was S, E, oh, this was a 14. Yeah, I just wrote it down wrong. That was a 14. N, D, space, C, A, S, H. Okay. So that's how you can decode the message using A inverse. Okay, so the last application we're gonna discuss is trying to calculate the least squares regression line for a given set of points. So basically, what we're trying to do with the least squares regression line is, so given some set of points in the plane, we're trying to find the line that best fits the set of points, in the sense that the sum of the squares of the errors, or geometrically, it's the vertical distance between the points and the regression line. So the sum of the squares of the vertical distances should be minimized. Right, so we want to figure out how to draw the line that's closest to the set of points in this sense. Okay, so the notation is going to be the following, right? So the least squares regression line we'll call f hat, or usually it's y hat. So the hat is standing for the line that predicts values, right? So a0 is the y-intercept and a1 is the slope. And we want to minimize the sum squared error, or SSE. Right, so again, each of these is the vertical distance in terms of the y values between the y values of the points and the y value of the predicted line. Okay, so basically to get the least squares regression line, we need to somehow calculate a0 and a1, right? So the y-intercept and the slope. So we can calculate these values using linear algebra in the following way, right? So first, we set up two matrices, which we'll call y and x, right? So the matrix y will contain the y coordinates. So it's just a column vector which contains the y coordinates, and our matrix X will be an n by 2 matrix where the first column is all ones and the second column contains the X values. Okay, so this is the setup, right? So we just set up these two matrices using the X and Y coordinates. And okay, so now how do I calculate A0 and A1? Well, we can calculate this matrix A, which contains A0 and A1, right? So you can see this is a 2 by 1 matrix by doing this matrix calculation here. So you multiply X transpose X, right? So you can see that X transpose is going to, so transpose switches the rows of the rows and the columns, right? So X transpose is a 2 by n, and X is an n by 2, right? So you can see X transpose X forms a 2 by 2 matrix. And so if you take the inverse of that, that's still a 2 by 2 matrix. Then X transpose again is a 2 by n matrix, and then Y is an n by 1 matrix, right? So if you do this multiplication together, right? So this thing, this inverse part is a 2 by 2 matrix. This X transpose is 2 by n, and then Y is n by 1. You can see that this becomes a 2 by n, and then multiplying this becomes a 2 by 1 matrix. Then the first entry here will give us A0, and this entry here will give us A1. Okay, so here we're not going to go into detail about how this actually gives us A0 and A1, but if you've taken a course in statistics where you go over linear regression, and you know the formula for calculating A0 and A1, you can see that you can kind of see where the formula is coming from in the following way, right? So this X transpose Y part contains the sum of the X's times the Y's, and also the sum of the Y squared. And then this X transpose X part contains the sum of the X's squared. The sum of the squares of the X's, right? So, and again, if you know the formula for A0 and A1, it's a combination of these things. And so we can produce A0 and A1 through matrix multiplication in this way. So one advantage of using linear algebra in this way is you can see that if you expand these matrices, you can extend this method to higher order polynomials instead of just regression lines. Okay, so in any case, this is how we get the coefficients for the regression line, and then we can also calculate the sum squared error, right? So the error matrix we can calculate as just y minus x times a, right? Because now we know a, and then once you have the error matrix, then the sum squared error is just E transpose E, right? So you can see that this is just a dot product, and so that this is a 1 by 1 matrix, which is just a single number. Okay, so this is how we're going to calculate the regression line. Okay, so let's go over an example where we calculate the regression line for the least squares regression line for the following set of points, right? So we're given 4 points. So these are the x and y coordinates. So first, to get the regression line, we need to set up our matrices y and x, right? So the matrix y is a column vector containing the y values, right? So we just list the y values in order, right? So it's 1, then 3, then 3, then 5, and then our matrix x, right? So the first column, if you remember, contains all ones, and the second column now has the x values, right? So that's -5, 1, 2, 2. Okay, so our matrix A is calculated as, so x transpose x, that thing inverse, and then times x transpose times y. X transpose x, this whole thing inverse, and then times x transpose times y. Okay, so in the PDF for this video, I calculated these individual parts by hand, the multiplication of these individual parts by hand, one by one, right? So first you calculate x transpose x, that will produce a 2 by 2 matrix, and then you take that 2 by 2 matrix, get the inverse for that, that's also a 2 by 2 matrix, and then you multiply it together with x transpose, and then with y. But to save time, I'm just going to put it into the calculator and calculate it all at once, right? So let's enter in the matrix for y. Y is a 4 by 1, right? So 1, 3, 3, 5. And B will be my matrix X, right? So what is that? That's 4 by 2. So 1, then -5, 1, 1, 1, 2, 1, 2. Okay, so that was my matrix B. B contained X, right? So, okay, so I calculate this out. I can actually do it all at once, right? So, parentheses, B was X. I need to transpose that. So this is, in math, this is the transpose. And then B again. Close parentheses, I need to take the inverse of that, and then times x transpose, which is B again, transpose, and then y, which was A. Okay, so I get this. Let's change it to decimal form, fraction form. So I get my matrix 3 and then 7 over 17. Okay, so this is my matrix A, right? So the first entry again is A0, the second entry is A1, right? So my regression line y hat is A0 plus A1 times X, right? So A0 was 3, A1 was 7 over 17. So I get this as my regression line, and we can actually visualize how good of a fit it is using the graphing calculator, right? So I can enter in the list of points in a table, right? So I go to stat, and then edit. So let's enter the x values. -5, 1, 2, 2, and enter in the y values 1, 3, 3, 5. And I can, okay, so I don't have a line yet. Okay, so let's plot the points. So I go to stat plot, right? So second, and then y equals for stat plot. Okay, so let's turn the first one on, and I want the scatter plot, right? So x values were in L1, y values were in L2. Right, so I can graph the points. You can see my 4 points like this, and then I can now enter in my line. So 3 plus 7 over 17x is my line, and you can see my regression line together with the scatter plot. And if I want, I can do zoom stat to get closer, to zoom in a little bit. And so this is what the graph looks like of the regression line. Okay, so that's what the graph of the regression line looks like. Okay, so now let's also calculate the sum squared error. Right, so our matrix E is calculated. We first have to calculate E, right? Which is y minus x times A. So let's store A in, say, C. Okay, so now I have to do the multiplication, right? So y, which was A, minus x, which was B, times A, which is C. So I get this as E, so 1 over 17, then negative 7 over 17, then negative 14 over 17, then what is that? 20 over 17. So those are my errors, right? So if each of these 4 points, right? So you see this one is mostly close, so it's 1 over 17. These two are below, so they're negative, and this one is kind of high above, so that's the biggest number, and it's positive. Right, so that's the vertical distance for each of the 4 points. And okay, so let me store this in E for error. Okay, so then now to get the sum squared error, I need to calculate E transpose E. And so let me just again use the calculator. So E transpose E gives me 38 over 17. Okay, so that's the sum squared error, and then this was the regression line. Okay, so before I end this, let me just make one comment, right? So let's look at X transpose X. What was X? X was B, right? So B, let's calculate that separately. So X transpose X is 40034. And so you can see that this 34 is the sum of all the X values squared, sum of the squares of the X values. You can check that. And then this x transpose y, so x transpose x was b, then I need the transpose, then y was a, so that's this many, 12 and 14. Right, so this 14 so this is the sum of the y's, right? So 5 plus 6 plus 1, so that's the sum of the y's. And then this 14 is the sum of the x times the y's. Like this. That's negative 5 plus 3 is negative 2 plus 6 is 4 plus 10 is 14, right? So that's the sum of the x times the y's. And so again, you can see that the different parts of the formula for the regression line comes through when we do this matrix multiplication.